Hey guys, we are doing 15.4, which is on arithmetic series. Different than arithmetic sequences. So we'll talk about what series are versus what sequences are. It says the first 4 rows of chairs are set up for a meeting. The seating pattern is to continue through 20 rows. How many chairs will there be in all 20 rows? And explain your reasoning. So looks like they have 1, 2, well, I guess they start with 4, and they go to 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. So you can see that they're adding 1 every time. So this is an arithmetic sequence if we just look at the numbers. But it says how many chairs will there be in all in 20 rows. So in all means you're going to add all of these together all the way up to 20. So when you're putting them all together, or you're adding them all together, that's what makes this a series versus a sequence. So it says we can use formulas to find series. A series is the indicated sum of the terms of a sequence. A finite series, like a finite sequence, has a first term and a last term, while an infinite series continues without end. So there's some examples of finite versus infinite series. An arithmetic series is a series whose terms form an arithmetic sequence. As shown above, when a series has a finite number of terms, you can use a formula involving the first and the last term to evaluate the sum. So we get this formula here for the sum of a finite arithmetic series. So the S stands for sum, N stands for how many numbers there are, how many terms there are, and then you have A1, which is your first term, and AN, which is your last term. So we just take N divided by 2 times the first term plus the last term, and that will give you your sum. Not now, proxy. Okay, so it says what is the sum of the even integers from 2 to 100? So you're just looking at even integers, so 2 plus 4 plus 6 plus all the way to 100. So if we look at our formula, Sn equals n over 2 times a1 plus an, we can fill in 2 of these pretty quickly right now, which is going to be our a1, which is our first term, so we can plug that in with the 2. And 100 is our last term. And then we just need to figure out how many terms there are. So if you're going from 2 to 100, if you divide each of those by 2, you get 1 to 50, which means there's 50 terms. So 50 divided by 2 equals our sum for the first 50 terms. So that comes out to be 25 times 102, which is 2550. So if you add up all of those first 50 even numbers, you get 2,550. So that is the sum of the series, or sum of the sequence. Okay, a company pays $10,000 bonus to salespeople at the end of their first 50 weeks if they make 10 sales in their first week and then improve their sales numbers by 2 each week thereafter. So 10, 12, 14, 16, so on. One salesperson qualified for the bonus with the minimum possible number of sales. How many sales did the salesperson make in week 50? How many in all 50 weeks? So the first week they make 10 sales. And then the second week they make 12 sales. And then it just keeps going up by 2. And then we need to figure out how many they make in week 50. Alright, so in order for us to find the 50th term, if you remember our formula up here, this gives us the nth term for an arithmetic sequence. So we just need to plug in 50. So a 50, because it's our 50th term, would be our first term, which is 10 plus 50 minus 1 times 2. So it goes up by 2. And that comes out to be 10 plus 49 times 2, which is, 98? So 108. So this is going to go all the way up to 108. Okay, and now that we know that, we can find the sum. So our sum, S of 50, we know that because there's 50 terms, 50 weeks, is going to be 50 over 2 times the first term, whoops, plus the last term. So we get 25 times 118, which is 2950. Alright, so in that one we had to find the missing, or the last term first, before we could find the sum. Okay. What was I talking about? 2,950. So they sold a total of 2,950 cells, whatever they're selling, I guess. Okay, this says you can use the Greek capital letter sigma, which is this summation. Looks like a E kind of, to indicate a sum. With it, you use limits to indicate how many terms you're adding. Limits are the greatest and least values of n in the series. You write the limits below and above to indicate the least and the greatest. So if you have this series right here, 3 squared plus 4 squared plus 5 squared, well, the pattern is you're taking that number and you're squaring it. So you say n squared here, and then you're starting at 3, so you say n equals 3, and it stops at 108 up here. So that's the notation for, oh, I guess it all says that right here, okay. So that's the summation notation. For an infinite series, summation notation shows infinity as the upper limit, so if it went on forever, it would just be infinity up there. To find the number of terms in a series, subtract the lower limit from the upper limit and add 1, so don't forget that, add 1. So in this case, you do 108 minus 3, and then you add 1. So we get 106 terms there. Okay. What is the summation notation for the series? So, first thing I would do is find the pattern, which in this case it's multiple choice, so it's nice. But you can just figure out which one of these works, 7n or 4n plus 3. But because this is arithmetic, it's linear, so it's going up by 4 each time, so that tells you your slope is 4. In order to get 7, you have to add 3. 4 times 1 plus 3 is 7. So it's got to be one of these two. We can cancel out this. So for A, we start at 1 and it goes to 51. For B, it starts at 1 and goes to 50. So probably the best thing to do here is just to plug in 50 and 51 and see which one ends up at 107. So if we do 4 times 50 plus 3, we get 200 plus 3, so 203. So that adds actually here. So we do have to go one more, so it's going to be this 51 here. That way it goes from 203 to 207. Okay. What is the sum of the series written in summation notation? And these are both finite sums, so we can find those. Well, at least for A, it's mx plus b, so it's arithmetic, so we can say s of, now remember we're going to subtract 70 minus 1 and then plus 1, so there's 70 terms here. 70 divided by 2 times first term plus last term. To do that, you just plug the numbers in. So if we plug in 1, we get 5 times 1 plus 3 is 8, plus 5 times 70 is 350, plus 3, 353, so 35 times 361, which is 12,635. Okay, and then for B, the problem with this is that it's not linear because it has this square here. So we don't know that formula, but if you notice there's only 7 terms here, so not too bad, we can just plug them in. If you plug in the first one, 1 minus 1 is 0, so that's 0 squared, plus 1 minus, or then you go to 2, 2 minus 1 is 1 squared, 3 squared, or 2 squared, I don't know, I see 2, 3 squared, 4 squared, 5 squared, and then if we plug in 7, 7 minus 1 is 6, so plus 6 squared. And then we just add all those together, so 1 plus 4 plus 9 plus 16 plus 25 plus 36. Well, these two make 10, these two make 40, so total we're at 50 now, plus this one is 75, plus that is 85 plus 6, 91. Sweet, 91 there. Okay. Alright, and then the last thing is I'm going to show you how to do it on your graphing calculator. So, on a graphing calculator, you can find the sum of a finite series by using commands from the list menu. So, for example, if this went to 70 here instead of 7, that would be way too long to write out, so you'd want to use a calculator. So what you can do is you can go to the list menu, see if I can pull up a calculator. Okay, so I'm also going to show you how to find a practice graphing calculator if you don't have one online. So you go to this website up here, and you select practice tests, and I just do college algebra. Go to continue. You have to go down here, you have to put in an email address, so just put in whatever email you want, and then answer this question. And then you get a code sent to your email. So let me check mine really fast. Okay, so mine is 91E95036. Okay, and then it's going to take you to this practice test, which you actually don't do the test. I'm just using it to get to the calculator. So continue. Next. Where is, oh, the calculator's over here. Okay, this is actually not the one I want. Okay, so I lied to you, you probably have to go to calculus. Same thing, 2 minus 1 is 1. And it actually tells you up here what graphing calculator you need, so I could have just read that, I guess. Okay, I'm going to put in this code, 6D797722. Continue. And then go to this calculator. Okay, so this is the calculator that I always use, which is basically a TI 84. Just looks funky. Okay, so where were we? Okay, so you're going to go to your list, which is the second stat button right here. So second stat. Okay, and then you need to go down to, or over to math. So tab over, go down to sum. Okay, and then choose sequence again, so go to the same place, except this time over to ops, operations, go down to sequence, because you're going to add up a sequence. And that gives us a series. Okay, and on this one it asks you for the expression first, so ours we want to do 5n, oops, that's not, okay, I guess I have to do it on here. So 5, we'll say x, plus 3, the variable is x, and then where do you start and where do you end? You start at 1, and you end at 70. And step, it just wants to know how much to go up by, so in this case just 1. If yours doesn't pop up with all these options, you would just type in as it's shown over here. So 5n plus 3, comma, n is the variable, comma 1, comma 70. Basically all the things we just typed in here. And then we get 12,635, which is what they got. So that's how you can do that on a graphing calculator. For those ones that are not arithmetic series, like the other one up here that we did before. I wonder if I can't edit it. Oh, maybe I can. Oh, yeah. Okay, so if we did like, and this might be too big, but if we did like x to the second from 1 to 7, yeah, that's going to be huge, but let's try it. Just kidding, it's not that big. Well, bigger than the other one, but so if you want to do like an x squared, you would just change that to x squared, and that would work for that. Okay, and that is all for arithmetic series. Next time we'll talk about geometric series, and that will be all from chapter 15. Alright, talk to you all later. Adios, folks.